Hi, my name is George. I'm an engineer on the XLA compiler team, and today I would like to tell you how to make your TensorFlow models run faster on the GPU using the XLA compiler. We'll start with a brief TensorFlow overview, followed by an overview of the XLA compiler, in particular for GPUs. Then we'll go through the usage detail of XLA and TensorFlow using JIT compile equals true, and how you can leverage to get great performance in your models. We will also cover the common use cases and the issues you might run into. Finally, we'll go through the benchmark results to see what kind of speedups you can expect. TensorFlow is a complicated system with many features, but we will focus on the ability to write simple NumPy-like Python code, which can then run with data parallelism and good performance on many different devices, be it CPU, GPU, or TPU. This is the running example we shall use throughout the talk. We are computing a mean of the sum of two vectors, where the first vector was squared and multiplied by 3. And then we run this computation with two random inputs. When we run this code snippet in TensorFlow 2 in eager mode on GPU, and if we open a profiler after a run, we see 4 separate CUDA kernel launches, one for each operation TensorFlow runs. Each launched CUDA kernel is parallel. It spawns many threads, and each thread will run the computation on some part of the vector we are operating on. For better performance, we can wrap the whole computation with TF function. When we wrap the computation with TF function, the TensorFlow will generate a TensorFlow graph from the Python code, which allows two things. First, the graph can be serialized, so it can be run even without the Python runtime. For example, if you're doing production serving. The serialization of the computation as a graph is shown on the right of the slide. But secondly, what we care more in this case, performance-wise, using the graph representation allows TensorFlow to perform a number of optimizations, such as constant propagation or fusing some operations together. However, the optimizations performed by TF function alone are driven by pattern matching and limited to a set of kernels found in TensorFlow. No new kernels will be generated during the optimization. But what if we could generate new kernels on the fly, specifically optimized for the task at hand we are using now? And that's exactly what the XLA compiler can do. XLA, which stands for Accelerated Linear Algebra, is a domain-specific compiler for linear algebra, which can emit code for multiple backends, including GPUs, CPUs, and TPUs. The compiler operates on high-level operations intermediate representation, or simply the HLO IR. XLA gets HLO IR as an input, performs optimization as a sequence of rewrites of HLO to HLO, and then emits executable code specific to a given backend. The HLO IR is a mostly functional language used for modeling linear algebra computations. It is designed to contain a relatively small number of operations. Unlike about 1,500 operations for TensorFlow, HLO has only about 50. The HLO operations are less domain-specific than TensorFlow ones, and they're designed to be composed with each other. The IR is strongly typed with the exact data type with shape and layout encoded into the operation type, and that strong typing allows it to be so optimizable. In this slide, we've given addition computation as an example of an HLO program. We get two inputs of size 100 by 100 with data type F32, and we compute their sum, which is the root of the computation. And the root of the computation is simply what the computation returns. And since, as we mentioned, the IR is mostly functional, it can be shown as a data flow graph, as seen on the right of the slide. The XLA compiler performs a number of optimizations on HLOs. One of the most important optimizations it does on a GPU is fusion, which is combining multiple computations together and not writing intermediate results to memory, drastically reducing memory bandwidth requirements. Let's show fusion on this example. So here we want to multiply a vector by a constant and then another vector. On a GPU, we can do so by launching two kernels one after another, one which multiplies the vector by a constant and another one which adds a second vector. However, this is not very efficient as we are writing the intermediate result to memory and thus wasting a lot of memory bandwidth. It would be a lot more efficient if we could hold the intermediate result directly in the registers and never have to materialize it. The fusion optimization does exactly that. As seen in the kernel on the right, we can combine multiplication and addition into a single kernel, which only has a single memory read and a single memory write, effectively halving the required memory bandwidth. Moreover, not only the fusion optimization reduces the pressure on memory bandwidth, it also reduces the number of kernels which have to be launched, minimizing the kernel launch overhead. Now let's go back to our running example, and let's see how the XLA compiler can optimize it using fusion. On the left, we see the initial HLO for the running example, with no optimizations applied. On the right, the compiler has applied the fusion optimization as shown by the red box. All operations within the red box are fused. They all run within a single kernel. No intermediate results materialized, and only the input and output memory allocations exist. After the HLO to HLO optimizations are applied, the backend-specific lowering takes place. Specifically for XLA GPU lowering to the executable code, it requires the following step. We start with an HLO IR. Then there are largely two possible code paths. Either the compiler generates a new kernel, the new CUDA kernel, then the emitter generates the LLVM IR, which is then converted by the LLVM backend to the PTX, which is compiled to the CUDA binary using the NVidia PTX-IS assembler. Or alternatively, the compiler might decide not to emit the code at all and to call the kublas or cuDNN library instead, if such an implementation is available. So far, we have seen how the XLA GPU compiler can be used to generate fast optimized kernels for your models. Now let's see how to use it from TensorFlow. Revisiting our running example, we have seen how adding the TF function decorator can be used to serialize the computation into a graph. The serialized graph can be compiled with XLA GPU by simply adding the JIT_compile equals true attribute to TF function, as seen in the running example on the slide, which will use XLA as a JIT compiler from TensorFlow. Let's see how the compilation pipeline is structured. First, the TensorFlow graph is converted to HLO using the TensorFlow to XLA bridge. The conversion and the compilation process is cached, so the results can be stored or retrieved from the compilation cache, also shown in this graph. Once the HLO is generated, the optimizations are applied, and the resulting kernel is finally run by the TensorFlow runtime. As we have seen before from the optimized HLO graph, we would expect only one large CUDA kernel to run, with reduction at the end. That's what we can verify dynamically with the profiler at runtime. We only get a single large kernel and nearly a 4x speedup compared to the eager example. Compiling a single line of Python is great, but how do we go about optimizing a larger model? Let's go through some more interesting examples, including expensive computations, entire training loops, multi-device training loops, and multi-device training loops where we cannot compile the collectives. In a simple case, we have a single computationally expensive function we need to run, either in your program or in the library you're writing. Adding JIT_compile equals true will compile the code inside, usually resulting in much better performance for all users of this function. However, most of the time, we are doing some kind of machine learning, and we are optimizing for some objective using some variation of gradient descent. In that case, it is usually best to compile the entire training loop, including the gradient calculation updates. This is what's done on the slide, where the entire code block to train the MNIST model is compiled. Note that the code taking the derivative and applying the gradient is also compiled. If it was outside of the compiled block, it can lead to worse performance, as many fusion opportunities could be lost. In TensorFlow 2.5, you can even compile the entire training step running with this distribution strategy. Currently, we only support the mirror strategy. In that case, you can annotate the entire training step with JIT_compile equals true and pass it to strategy.run. There are some caveats. We currently do not support SPMD, so multi-device compilation will require as many compilations as you have devices. potentially resulting in slower compile times. Alternatively, if you use collective separations which are not currently compilable, such as Horovod, you can refactor your code to separate the train step into a compilable part, a compiled step in this case, and leave the apply gradient function uncompiled. Then the train step, which calls the compiled step function, is passed to strategy.run. In these 4 examples, we have seen where JIT-compile equals true can be applied to improve the performance of your model. To find good annotation spots, we recommend using the GPU profiler to figure out which sections of the model contain many smaller kernels and can benefit from the optimizations. Usually, the larger the annotated compiled block is, the better the performance. Changing and refactoring the model you have might not always be feasible. For these cases, we have developed the Autoclustering mode, which automatically identifies parts or clusters of the code inside the app.function which can be compiled. Then the Autoclustering mode outlines these clusters and replaces them with TensorFlow ops invoking the XLA compilation. To activate the Autoclustering mode, either use the environment variable tf_xla flags set to tf_xla auto_JIT equals 2, or use the tf.config.optimize.setJIT API. Even though using autoclustering is fully automatic and does not require any model changes, it can lead to bizarre performance cliffs, where seemingly small and consequential changes in the model lead to large changes in clustering decisions, completely changing the performance characteristics. For these reasons, we recommend JIT-compile equals true usage, as it has a simpler, understandable mental model. Everything inside the JIT-compile equals true block is always compiled if it runs. Now that we've covered the use cases, let's go through the limitations of JIT-compile equals true. We've briefly discussed already that not all operations are compilable. Let's cover that in a bit more detail. Furthermore, we have previously mentioned that the XLA compiler requires shapes to be static. Let's see how that interacts with dynamic inputs in TensorFlow. As we said before, TensorFlow has roughly 1,500 operations. Only about a third of them are compilable. While for some ops this represents future work, in many cases the op is inherently uncompilable, for instance if it's a heavy image decoding op which could also perform some I/O. When an uncompilable op is found inside the JIT-compile equals true block, an exception is thrown to the user indicating an error. Moreover, the exception will contain a stack trace indicating exactly where the uncompiled op was defined, so you can refactor your code. So let's see that in the example. In this case, the function load invokes an operation to read the file, which is not inherently compilable with XLA. If you attempt to run such a function with JIT-compile equals true, you will get an invalid argument error exception with the attached stack trace pointing out the definition of the uncompilable op. This information will help you to refactor the function in order not to try to compile the uncompilable op, as was done in the previous example, avoiding the uncompilable collective. The second limitation of XLA is the requirement of shapes to be static at compile time. The TensorFlow inputs to the function can have different shapes from run to run, which is not something representable by a single HLO program. However, since XLA is a JIT compiler, it can just recompile every time it encounters a new shape. In practice, this tends to work well, especially for batched inputs with a constant batch size. However, if the shape changes very often, the recompilations can add up, causing unexpected latency. For instance, in the example on this slide, if you run the example multiple times with a shape of 10 by 10, only the first time you run it, the compilation is necessary. But then if we change the shape to be a matrix of 100 by 100, we would need to recompile. And all compilations are essentially cached forever while your process is running. In addition to constant shapes, XLA requires certain arguments to be fixed at the HLO level. For instance, the axis argument of argmax. Changes to such argument at runtime results in recompilations. When such must-be constant arguments are computed inside the function, all parameters potentially influencing the computation are marked as must-be constant. Changes to such parameters would require recompilation. For instance, in the example on this slide, if we change the second argument to f, each time we change it, we would need to recompile it. And if the second argument was computed using multiple parameters, any change to any of those parameters would require recompilation. Shifting gears a bit from the limitations of XLA, let's talk about the ways you can look under the hood of the TF XLA stack by inspecting the generated HLOs. There are a number of reasons you might want to look at the generated HLOs of PTX files: to see what fusions have taken place, to verify that the aliasing has happened, or to simply file bugs when you see some weird behavior or unexpected performance. For the compiled code, you can also look at the generated PTX files to understand their performance characteristics. We offer two ways to inspect such files. First, you can run your model with XLA flux environment variable containing the XLA dump to flag, pointing to a directory where the generated files will be dumped. Alternatively, you can use the experimental getCompiler IR API on the JIT compiled functions. Let's see a few examples of usage of this API. Using the getCompiler IR API, you can expect the HLO, optimize HLO, or the graph and graphics format for a compiled function. To plot the graph returned by the optimized HLO dot format, you can invoke the graphics binary on it, and you will get the HLO graph rendering in the same format you have seen throughout this talk. Note that in order to generate the HLO, the input arguments to the function need to be fixed, as changing certain arguments might require compilations. Now let's go through some benchmark results to see what kind of speedups you can get from XLA. We are reporting our results on the TensorFlow Model Garden repository, which you can find on GitHub under TensorFlow/models. All the models we report are run on 8 V100 NVidia GPU cards with data type set to FP16, which is most often used while training. In order to benchmark with JIT compile equals true, we are making only a single code change to the model, which is simply adding the JIT compile equals true to the step function. And often that due to fusion, we were able to decrease the memory requirements. We were bumping up the batch size, which we could not do before XLA. And for autoclustering, no changes at all were applied except of adding the environment variable. So those are the data points that we got. And we can see that with JIT compile equals true, we could get a speed up from 1.2x to 1.9x on a variety of models, including BERT, Transformer Resonant, and Mascar CNN. The increase in performance with autoclustering was slightly lower from 1.2x to 1.5x, and no changes to the model were required. You can see that in one case, the performance actually got slightly slower with autoclustering, which can actually happen. So since it's a fully automated process, which it's hard to see exactly what it's doing. So that's why it's another reason why we promote the usage of JIT compile equals true. Independently from the model garden, NVIDIA maintains their own repository of models, and they kindly have given us their data, which for the speedup they got when running with autoclustering and without it. All NVIDIA benchmarks are done on 8 800 NVIDIA GPUs, again using the FP16 data type. In these benchmarks, we see a similar speedup in the range from 1.2x to 1.7x on the variety of models. That's all for the benchmark results. Now let's go through some future improvements to the stack we are planning and the conclusion of this talk. We're always working on many different areas of TensorFlow and XLA, and here are some sample projects. And of course, this list is very incomplete. We're in the process of rebasing the XLA GPU compiler stack on top of MLIR, which is a reusable open source compiler infrastructure project. With that work, we aim to get more complex reusable emitters for the compiler, as well as true dynamic shape support, and many other improvements. On the TensorFlow side, we are looking at the automatic handling of uncompilable ops, so the JIT-compile equals true could be added to more functions, including those containing uncompilable operations. Additionally, we are collaborating with NVidia to deliver Horovod compilation with XLA, so that the entire training step can be compiled when Horovod is used. In conclusion, as you have seen, using the compiler can greatly improve the performance of your models. We recommend using the profiler to find the set of kernels which can benefit from fusions and other optimizations, and annotating the corresponding code block with JIT-compile equals true. Usually, the larger the block is, the better the performance. After the model is annotated, we have shown that the performance boost is usually in the range of 1.1x and 2x. With that, I thank you for your attention.